Alright, so unfortunately, adiabatic didn't get recorded during class. So here we go, take 2. Our fourth type of state change of an ideal gas is called adiabatic. So we've already had one type of state change where we kept the volume constant, that was isochoric. One type where we kept the pressure constant, that was isobaric. One kind where we kept the temperature constant, that was our isothermal. So what the heck else is there to keep constant? And it turns out there's nothing left to keep constant. So in an adiabatic change of state, everything is going to change. That's why it doesn't start with iso. So adiabatic, what do you call it? The best way I have to remember that, well, adiabatic means there is no heat exchange between the system and the surroundings, right? No heat exchange whatsoever. So by definition, the Q is equal to 0, end of story. Okay, that is the definition of adiabatic. I think it comes from the A is Greek for no, that is Greek for through, and that is Greek for pass, or vice versa. So it kind of literally means no pass through, so no heat can pass through the container, right? So no thermal energy exchange whatsoever. All right, so let's deal with that on a pressure-volume diagram. So pressure has to change, volume has to change, and the temperature has to change. I'm going to start by putting up our isothermal curve, but I'm going to do that. I'm going to put a few different isotherms up. I'm going to put our isothermal for a few different constant temperatures. Okay, so those are just isotherms. An adiabatic change of state has volume changing, it has the pressure changing, and it has the temperature changing. So what that's going to look like is an extra steep isotherm. So it's going to have a similar curvature to our isotherms, but it is going to be steeper. It does have to hop from one temperature to a different temperature. All right, so this would be an adiabatic expansion, or an adiabatic contraction. An adiabatic contraction would just kind of go the other way. All right, so that's what it looks like on a pressure-volume diagram. In terms of our first law of thermodynamics, we've already established that the Q has to be 0. Absolutely has to be. If we have our adiabatic expansion, right, so if we just have this blue one where the volume increases, then we know that the work done is positive. If the volume goes up, then the work is positive. And if the work is positive and the Q is 0, then the change in internal energy would have to be negative for the adiabatic expansion. So we'd have to be going from a hotter temperature to a colder temperature. Now, the other thing that might pop out at you is that the change in internal energy and the work do have to be equal but opposite directions. So our gas in this instance is doing work, the volume is increasing, but all of the energy that it requires to do that is coming from the gas molecules themselves. None of that is coming from external energy that's entering the system. Okay, so that's pretty much all there is to say about adiabatic. There are 2 other extra things that I'll throw in. One extra thing is that a very fast change of state is approximately adiabatic. So if we contract, if we condense, compress a gas, if we do that fast enough, we don't really allow sufficient time for thermal energy to exit or enter the system. So any fast change of state is approximately adiabatic. That's why in our ideal gas lab last class, I said, all right, press the syringe in as quickly as possible and take the reading as quickly as possible. I didn't want there to be sufficient time for heat to enter the gas from the surroundings, or exit. All right, so that's adiabatic. Now, in the next clip, you're going to hear me talk about thermodynamic cycles, and then I don't know how long those SGA speeches took today. You might not really have time to work on problems in your foursomes. If you don't have time to do that, you don't have to do it for homework. but they're all good problems, and it would make sense as a study tool maybe for your test to do those.